This video is for Chemistry in the Earth System, Unit 2.5, Periodic Trends. Today's essential question is, how can the observed periodic trends in reactivity of an element be explained? Our first main idea, electron configurations and the periodic table. The periodic table was originally developed as a way to organize elements according to their properties. As chemists learned more about atomic structure, they began to understand that the arrangement of the periodic table should also reflect the arrangement of the electrons in atoms. Periods correspond to the energy levels occupied by electrons. Elements in period 1 have electrons in only one energy level, whereas elements in period 2 have electrons in two energy levels. Elements in period 3 have electrons in three energy levels, and so on. Elements in each group have the same number of electrons in their outermost energy level. For example, all alkali metals have one electron in their outermost energy level, and all alkaline earth elements have two electrons in their outermost energy level. Our next main idea, valence electrons and reactivity. The outermost electrons of an atom are called the valence electrons. These are the electrons involved in chemical reactions. Elements tend to react with one another to either donate, take, or share electrons in order to achieve a filled outer energy level. This makes them more stable. Metals tend to lose electrons, and nonmetals tend to gain electrons in order to achieve a full outer level. It is this tendency to gain or lose electrons that determines how reactive an element is. The greater the tendency to gain or lose electrons, the more reactive the element.
When two or more atoms join together, new chemical compounds are formed. The chemical bonds between these atoms result from interactions among the valence electrons in each of the atoms. The valence electrons are found in an atom's outermost shell. When atoms share valence electrons, they form covalent bonds. Forming a covalent bond creates a more stable molecule. Here, each hydrogen atom contributes one electron and shares one from the other atom, giving both outer shells two electrons. Other groups of elements that don't have full outer shells, such as halogens, also make molecules with covalent bonds. For example, chlorine has 7 valence electrons in its third shell. It needs 8 to become full. Hydrogen and chlorine both have incomplete outer shells. So these two atoms can form a covalent bond by each sharing an electron to form hydrogen chloride. Double covalent bonds are also possible. For example, oxygen atoms have 6 valence electrons in their second shell. A molecule of diatomic oxygen is formed when two oxygen atoms come together and share 2 electrons with each other, so both atoms are filling their outer shell. Carbon dioxide is another example of a molecule with double covalent bonds. Carbon atom has 4 valence electrons. It shares 2 electrons with one oxygen atom and 2 with another. So there are 2 double covalent bonds in carbon dioxide, one between the carbon atom and each of the oxygen atoms. In summary, covalent bonds are formed when atoms share valence electrons. Double covalent bonds are formed when 2 pairs of valence electrons are shared. And when the electrons in 2 or more atoms bond together, new chemical compounds are formed.
Explaining trends in chemical reactivity from group to group. Elements within the same group have the same number of valence electrons in their outermost energy level. Therefore, the general pattern of reactivity seen between elements within the same group can be explained by this similarity in valence electrons. For example, all alkali metals have one electron in their outermost energy level. We can explain their highly reactive nature from this feature. Because they have only one s orbital electron to lose to achieve a filled outer energy level, these electrons lose this electron readily. This explains their high reactivity. In the case of the transition metals, the tendency to react is much less. Most of these elements have filled s and p orbitals. Only their d orbitals are partially filled. It is energetically less favorable for atoms with partially filled d orbitals to react. As a result, these metals are comparatively stable. With respect to nonmetals, the most reactive elements are the halogens, which gain one electron to form a filled outer energy level. Nonmetals in group 15 must gain 3 electrons, and those in group 16 must gain 2 electrons, which is less likely to happen, and this makes these atoms less reactive. The pattern that emerges from these observations is that for many atoms, the closer the atom is to being able to achieve 8 valence electrons in its s and p orbitals, the more reactive it is. Of course, at the very far extreme are the noble gases. These elements have filled s and p orbitals. Their inert character results from this feature because they have a tendency to neither lose nor gain electrons. As a result, noble gases are very non-reactive. Explaining trends in chemical reactivity from period to period. We saw that reactivity increases as we go down within a group of metals and decreases as we go down in a group of nonmetals. But why is that? The answer has to do with the ease of gain or loss of valence electrons by that element. We can take the alkali metal group as an example. As you move down this group, the number of energy levels increases. As these energy levels add layers to the structure of the atom, the valence electrons are located farther away from the positively charged nucleus, and more electrons are present in their inner energy levels. These inner electrons shield the outer electrons from the positive nuclear charge. With so much shielding, the valence electrons have less pull or feel less pull from the nucleus and can move away with greater ease. Because alkali metals lose electrons to achieve stability, greater shielding results in greater reactivity. If we examine the halogens as an example of the nonmetals, we observe something different. As we move down the group, the number of energy levels increases just as with the metals. This again increases the shielding of the outermost energy levels from the nuclear charge. The nonmetals, however, gain electrons to achieve stability instead of losing them, and the increase in shielding decreases reactivity in the lower periods of a group because the pull of the nucleus is now limited. At this point, you should be able to generate a full and appropriate response to today's essential question. How can the observed periodic trends in reactivity of the elements be explained?